Good evening, ladies and gentlemen. Welcome to the West Midlands. Got a lot of feedback there. Welcome to our West Midlands technical lecture. I think it's number 2 in this series. Tonight is a little bit different. I think we're used to technical presentations about products, about applications, feeders, filtrations, casting problems. But tonight, you can see the question. Can the tension of increasing productivity, reducing costs, and launching new products with a simultaneous increase in a shortage in the skilled workers be resolved? Quite a challenging question, which I think if we could have the answer straight away today, we could all be very successful. But I'd like to invite Jurgen Schmiezek, close, yeah, excellent, from the Chief Growth Officer from Tvarit to try and answer this question. Jurgen, please.
Ladies and gentlemen, it's a great pleasure to be here and a great honor. Just in advance, I'm not a foundry expert, right? And so what we are talking right now is the application of a new technology which is dealing with lots of data. So before we start and before I go into the presentation and give you more insights about that, just maybe raise your hand if somebody has heard about artificial intelligence called AI. A few of them, right? So for those who haven't heard about that, let me just give you a quick intro before I start my presentation, just to give you an idea what artificial intelligence is. First of all, it's not about the replacement of human, right? So this is a myth. And artificial intelligence is basically mathematics. It's statistical calculations about huge numbers of data points to find correlation, to find patterns within a mass of data. And that's why it's called artificial intelligence, because the human brain is normally able to calculate and to reproduce patterns, what we have learned in the past quite good. But artificial intelligence is basically not that powerful as a human brain, but what it can do very, very good is to find correlations and patterns in mass data. And I'm talking about trillions of combinations. I come to the point later on. So just keep in mind and give you a quick example. Everybody's talking about autonomous vehicle, so autonomous driving vehicle. So what those cars need to learn is actually, just to give you a simple example, a shadow of a human being. So the car needs to learn from the camera data that it is receiving that there's a difference between a real body of a human being and a shadow. So it is okay to drive over a shadow, but not over a human being, right? So this is the complicated story behind artificial intelligence, and it is intelligence, but it's reduced on statistics and mathematical calculations. Okay. So let me just, today I want to give you a short intro about us, and the next following slides is about the actual challenges that we face, and you all know. Why I'm doing that is to come to the point why an artificial intelligence, why AI could be an essential part for the foundry industry and the casting industry worldwide. And last but not least, I would like to make it very, very clear why AI in production is not the same than autonomous driving. And last but not least, I would give you some examples what we have solved and what we have done so far in the casting industry. So we are driven by the vision of creating a sustainable and zero waste manufacturing. And why we are doing that is just simple, because we believe in the unbelievable high value of zero. For us, zero has a high value, an unbelievable high value actually. And why? Well, basically, when we thought about resources, when we thought about material, humans, machines, energy, the waste of those resources is creating a huge loss. And on the opposite, savings those resources creates a high value. So in every case, when we are able to save those resources, we create a high value. And that high value is not only in terms of the financial impact, it creates a freedom to invest. Invest in a company, invest in a generation, invest in the future. And that's why we're driven to create a zero waste manufacturing, because by applying that zero waste, we're creating a high value. As I said, Tvarit is focused on creating and developing an industrial AI. So we are only focused on creating an application of artificial intelligence in industrial environments. We're doing not autonomous driving. We do not Siri in mobile phones. We are just doing industrial AI. So we are based in Frankfurt in Germany with a subsidiary in India. So we are a German-Indian company, deep tech company so-called, founded in 2019. And at the moment we're 60 people, and we call them AI engineer. Why? Of course, they have a data scientific background, but coming from the manufacturing or production environments and having an engineering degree. Why is that important? Because we need to understand the processes. We need to understand production. And if somebody has not the understanding of those processes, it would get difficult. At the moment, so for the moment, we have about 55 projects delivered worldwide with clients in all areas, from, you see the blue spots, from India to Czech to South Africa, Brazil, Mexico, US, mainly in the area of casting, but also in metalworking and metal forming, for example. I come to the specialization right away. We have also created some awards and won some awards, but yeah, that is nothing important. More important is how we work. So first of all, we focus on innovation. We want to be the leading edge. Therefore, we do a lot of R&D projects. At the moment, we're having 6 R&D projects running with institutes like Stanford University, the IIT in Mumbai, which is the let's say the pendant to the MIT in US. So this is the core competency, and I come to the point later on with this differentiation why there needs to be an adaptation of AI in production processes. We have actually 2 patents in that area, and our goal is to have at least 2 patents every year. So that's why R&D is a very strategic pillar of our company. The second one is a long-term perspective. We are having 2 advisory boards. We are a young company. And as I said, we are not the expert in foundry. We're also not experts in metalworking. But we have 2 advisory boards that complements us, especially in those areas where we need special know-how and especially also seasoned know-how, like in the casting industry. So we have a board. You see that in different areas of competency. We have from the foundry industry, Mr. Johannes Messer, maybe somebody of you know them. We have Bas van Germet from Gemco in the board, but we have also from different areas in different department areas, advisors that help us to create a long-term sustainable company and business model. And last but not least, when the client signs a contract with Tvarit, he signs also an insurance for the future that we gave him to operate the software regardless of our future. So regardless of our future, of the company's futures, we make sure that the software, the technology is surviving regardless of our future. Why are we doing that? Because we're a young company, we're a startup, and this is the technology we're dealing with is a strategic decision. It is changing the way that foundries and casting industry is working. And so we need to create a future-proof and a future guarantee. Now, coming to our technology, just in short, before I come to the challenges, I will just roughly explain what we're doing. We're just doing 4 use cases around that zero waste manufacturing. Reduction of scrap, reduction of energy, increasing the machine uptime, and creating an energy efficient production planning. We are just doing those 4 use cases. We're not doing anything else. And our technology is an analytical technology that is not providing just insights. So people that are using TIA, our Tvarit Industrial AI platform, will not get just an analysis. What we provide is so-called prescriptions. So that means our technology is able to not only recognize patterns, but also provide prescriptions in order to recommend, for example, an optimal set of parameters to an operator by learning out of the past. That is just a rough explanation. And again, just to highlight the 4 use cases, and then I will immediately start the talk about the challenges. So first of all, the reduction of scrap, I think everybody is familiar with it. The second one is, besides the scrap, at the moment, our really best-selling use case, reduction of energy. This is not just an energy management or energy monitoring. We're talking about the lowering of energy consumption in respect of the quality of the casted product. Because it's easy to reduce the energy. Just turn off the furnace, right? Then you save a lot of energy. But then you have a problem with your casted products, right? So the question is, how do you lower the energy on a part level to a maximum without corrupting the quality? This is what we are doing there. Of course, the machine uptime, I think everybody is aware of the OE. And the last one is the energy efficient production planning. So there is just one example. How do we make sure that, for example, energy consuming machines are utilized in an optimal way, for example, in combination with solar power, batteries, and something like that? This is something for the future, but not the topic for today. Give me just 2 minutes about explaining why we're specialized in casting in a different way. The platform that we have, at the moment, we have more than 160 AI modules based on our experience in the past project, pre-defined our platform. So we're not starting from scratch. That's the first topic. On top of that, we have built the 4 use cases I just shown you. But now, those 4 use cases are again verticalized. So we are creating for every individual industry a version of each use case. Why are we doing that? Take casting. We're not talking about just casting. We're talking about HPDC. We're talking about LPDC. We're talking about iron casting. We're talking about steel casting. We're talking about gravity. We're talking about centrifugal casting. We talk about sand casting. So we have in casting multiple production processes and types. And each type is completely different to the other one. So what we're doing is, in order to achieve great results in a very quick time, and come to the point later, for us, quick time means 2 to 3 months. How do we do that? We implement process and domain knowledge for each process and production type in our technology. So we know what parameters are usually used in LPDC. We know to 60–80% what we use in HPDC. We know when it comes to iron what we do. Again, we are not the expert, but we are implementing the knowledge from our past projects in our technology in order to create fast results. Now, when we talk about the actual challenges, why could AI be an essential part? This is just a quick go through all the challenges that you already know for sure. But the conclusion out of it is exactly the question that was highlighted in the first slide. So first of all, talking about energy costs. Since you see the graph, this is the price index for carbon trade emissions, carbon prices for the index price emissions. And you see, since 2019, we have an explosion in the carbon emission rights. So in the next 2 years, this goes to 35 years, we will end up in 50 years for sure. And even more, the amount of emission rights is reduced from this year by 2.2% or 2.6%. EU is not sure how much they reduce it annually. So there will be a lack of emission rights for sure, with a higher price in the future. The second one, of course, everybody knows, the price explosion, not only in the power, but also in the gas, the red ones. The gas has reached a price increase of nearly 150% just in the last 4 years. That's really, really serious. But what is the solution? Here you see the standard operation procedure if you implement energy management according to ISO 50001, right? It's a standard implementation process. You plan it, you do the implementation, the operation, you do the monitoring, you do corrective measures, and so on. Takes you 6 to 12 months at least to implement. I'm not talking about achieving results. And what you need? Experts. Okay? The second one is, for sure, since every year the OEM and the clients are demanding higher productivity and higher margins. That means, especially for the whole industry, we are still dealing with an average of between 65 and 85% OEE since years. And why is that? Because continuous improvement programs has limitations. Why are those limitations? Let's look on those programs. All of them are based on Kaizen. Name it as you want. Lean management, whatever. It's all the same principle. And the principle is always the same. Plan, do, and check and act. It's an iterative approach. And this iterative approach is driven by experts. And this costs time. So of course you achieve a higher productivity. You have already achieved a higher productivity over years. But you know how long it took you. Now coming to the third one, new technologies. In 5, 6, 10 years, we will not have any combustion engine anymore, with all the related consequences for the casting industry. Okay, there were new products. Take an e-car. The e-car is having new technologies, new designs. It gets more complex. It gets more lightweight. It gets more in direction of maybe aluminium or composited, whatever. But anyway, there will be no technologies. But that means new geometries. And the new geometries need new lines, new assets. And that is consequently leading to new processes. And what do you need? You need to stabilize those processes. And you know that every new ramp up of a process creates a lot of heavy work, right? And what do you need for that? Experts. To stabilize and to maintain the processes in a optimal window. Now, we are facing a lot of issues where we need experts. The problem is we do not have experts. And they're getting even less. So now coming to the point or the dilemma, we're having new products, which is good. The future in casting is, in my opinion, just the beginning at the moment. There will be a lot of new casted products in an electric vehicle. But for new products, we need investment. The average EBITDA margin in the casting industry is 5 to 6%. So in order to be able to invest into new lines, in new products, in new technologies, in new people, we need the capability to invest. That means we need to reduce the costs and increase the productivity on the same side. And that leads again to experts. Now coming to the most critical topic at the moment, where, for example, also a lot of clients we talk to in Eastern Europe, they don't know if they exist next year. They just tell us, we would like to do a project, but we do not know if we exist next year because our government is not able to do any subvention or doing some financial support. So it is a very critical situation. And of course, we need to reduce the energy anyway. We need to also find new ways of get rid of natural gas, maybe. But in any case, we need experts for that. And the experts are the missing gap. We do not have experts at the moment, and to make it really drastical, this is the actual data. You see it on the left-hand side. This is the statistic from Eurostat, both from EU and non-EU. The job vacancies, just 2020. You see the explosions of the job vacancy across Europe. It's not talking about just UK or Germany. We're talking about EU. And on the right-hand side, this is for UK, the actual job vacancy, and you see it. The fourth one, I'm really sorry, the resolution is a little bit bad. The fourth one is manufacturing, 91,000 job vacancies. It's the fourth besides healthcare. So the dilemma that we can face in an actual situation, we talked about that with you know all the challenges also from the past decades. It's nothing new. Productivity increase, energy cost, new products. Nothing is new. The challenge at the moment is it is completely at one moment combining a combined situation where all the challenges must be solved at once. And the critical topic is everything is relying on experts. So now the question comes, can be AI an essential part of the solution? And to answer that question, let me give you an example which you know, everybody, better than me. So this is, I'm really sorry about the resolution. This is an Ishikawa and root cause analysis for HPDC. Why do I use HPDC? Because it's for us one of the most complex one with most influencing factors that we have considered so far. I'm not talking about that the other ones are not having influencing factors in the same manner, but this is just an example by that. Why I use that? you as foundry experts, as foundry engineers, as experts for many, many years in the industry, you have a huge background and knowledge and experience when it comes to resolution of quality defects. And that background, that experience gives you the possibility to exclude, based on your experience, a lot of influencing factors if you analyze the root cause for a defect. It could be right. It should be right. But in most cases, it is right. But given the fact that you have decades of experience, but then you have still a lot of influencing factors still open. And what the industry is doing, not only here, but everywhere, they start with one parameter and they change the parameter. Why just one? Because you get one result. If you change two, you have the 50-50 chance what was the influencing parameter. So you have to go one by one to eliminate the influencing factors. But everybody knows that what is the situation in casting? We have multiple influencing factors. And most probably, they come not only once, they come 2, 3, 5 parameters in one situation. And even more, the values for those parameters are changing. They're not the same. They're volatile. And tomorrow, there's a different pair of grouping. And if we just take 20 parameters at once, there's a combination of 2.4 trillion pairs of parameter out of 20. I'm not just talking about 30, 40, or 60 influencing parameters. I'm just talking about 20. So it's the sheer mass of combinations that creates the question, how do we solve that? And our answer is with a technology that is capable to gather all information simultaneously in a multidimensional way. I created a very, very, very abstract example, and it's not the complete casting process, but I want just to give you the principle how we are working with the data. So we start with gathering the material data in the melting shop over the whole process and casting cell, get the set points, get the actual data, until the QA. And by gathering those information, we create, let's call it a digital fingerprint. And this digital fingerprint is unique. At that moment, when a part is casted, we know every parameters. We log them, we store them, and we link them with a timestamp and an ID, a unique identifier, a DMC or whatever. And when it comes to the QA, and the part is considered as not okay, we know what was the parameter set points. What was the combination of all parameters to that given time? But also when it's okay. And now think about thousands of parts produced. We create a knowledge that you as experts have gained over the years, over the decades, but just in a couple of months, by identifying always the correlation between not okay and okay, and logging all influencing parameters in a database, and create per part a digital fingerprint. Okay, and how does it look like? You see here just a simple illustration of what I mean with the good fingerprint and what the fingerprint is usable. Here on the left-hand side, you see, I think it's a green one. I hope you can see it. The dark green area here. This is the optimal window for a casted part. In this example, this is a client example. Doesn't matter what kind of part, but this is the optimal window, right? So here, the green part, the dark green part, is the optimal window for operation. Every cross that you see here is a casted part with an individual set of parameters. And that's the reason why they are spreaded, because the parameter changed. Temperature, pressure, humidity, whatever. So you see this results in a scrap because it's outside of the perfect window. What we have applied here is most of the crosses are within the dark green area because we propose the optimal setting because of our learning, what leads to a good part and what leads to a bad part. And we provide the recommendation based on shifting parameter windows that we observe in real time on the machine. So by listening to all the parameters that comes from the machine, from the processes that we learn, we observe a shift in the window immediately. And we inform the operator and say, hey, guy, you need to adapt the temperature, the solidification pressure, the heat temperature or the heater element and the holding furnaces, the mold temperature, whatever. So we provide him parameter and say, okay, change the temperature or increase the solidification pressure from 550 to 600 millibar, whatever. And that leads to this optimal window of parameters. And below you see the upper line is the scrap, the defect rate without TIA. And the green line below is 50%, I think, not only 50 degrees in average, the defect line with application of TIA. So in summary, we have a lot of data points that are relevant to control and stabilize a casting process. Human beings cannot, no one in the world can control those amount of data points in real time. In order to achieve that, we have to use a technology that is able to correlate trillions of data points. And by that, we're creating stabilized processes because learning from the parameter set points that leads to a good or a bad part. And by that, oops, I'm sorry. What we're talking about is human-empowered AI. So we empower the operator by giving them an experience that is learning from trillions of data points from thousands of casted parts. And by that, we are able to address all the areas by an empowerment, by an augmentation of knowledge that is learned from the production and applied to the operator. And by that, we can preserve not only knowledge, we can also make sure that the knowledge is expanded and secured for the future. And by that, we can also apply operators and operators to the machine, which are less trained, because the technology is able to augment the parameter set points and recommendations to that to a certain level of the knowledge. So let's just focus again on production processes. Now, you heard a lot of data points and correlation and all this stuff. Now comes to the point why traditional AI is not working in production processes. Complete opposite. I'm happy to have Magma with us because they're doing since many years this one here. You all know simulations. We know simulations for decades. So simulation works on a physical basis. They take all the physical properties, the domain knowledge and all this stuff, do calculation and regression curves, assumptions, okay? This is what I've explained to you about AI. You see, AI has nearly the same accuracy than a simulation. A simulation is not 100% perfect. It's not 100% accurate. Why? Because of assumption. The good news is AI is neither. Why? Because AI works with data. But what if you do not have data? You cannot measure a solidification. You cannot measure the injection process of the melted metal. So the AI is blind. What an AI is not able to measure, an AI could not correlate. So we came very early on that point, and what we have invented, and this is our first patent, is called hybrid AI. We just combined the two worlds. Just is easy to sell, but basically what we did is we combine the physical simulation in our AI model. That means in every area where the AI is blind because no data available, we enrich the AI model by physical simulation and calculation. But even more, we are feeding back live production data in the simulation, because a simulation needs an expert that enters all the values, all the assumptions, all the values, all the parameters. And that is a snapshot. What we're doing is we're feeding back the live production data, which we gather in real time, and by then enrich the simulation and make those calculations even more precise. And in this combined approach, we achieve not only a very production realistic or production engineering realistic accuracy, which is nearly 100% accurate. It is a representation of the physics and the AI combination. The second point is just something that is very quickly a topic not really of interest in that. Just the second patent we have is this dealing about scalability. Normally, when you have multi-machines line, you have to create a model for each machine and for each product, which creates, if you have 10 and 30 or 1,000 products in your portfolio, it creates a massive effort. Nobody will pay that. So what we have, sorry, that was too fast. What we have created is called transfer learning. So we transfer the learnings from previous model to a machine and another product, but just, let's say, copy and paste the learnings from the first model to the next model. So in summary, what we have learned is, first of all, zero waste means we need to take care about the holistic production processes and all waste that occurs, machine, human, material, energy. Second, by developing the two patterns, the hybrid approach and the transfer learning, we are able to serve production processes in a very efficient way. And last but not least, the scaling of those projects can be done in 1/3 of the time of the initial project. Now, let's take the last minutes and talk about some use cases that we've done to give you a real-life example of the application of TIA. The first example I've brought with you is from LPDC, and it's about reduction of rejects. The starting point was automotive tier 1 supplier based in Germany, producing 10,000s of parts or millions of parts actually every year. And the problem statement was scrap, and to be precise, 12% scrap in total based on shrinkages and gas porosities. Whereas the gas porosity was the major contributor to the scrap rate with nearly 60%. And the question was just, how can we avoid that? Because the main quality inspection in order to identify the scrap was done in the X-ray. So at the end of the process, there they identify most of the scraps, which leads to a huge problem, because until they have identified the scrap, they have produced hundreds of parts. So the project was, the target for the project was a decrease of minimum 30% in just 2 to 3 months of the scrap rate. How did we? So first of all, we collected the machine data, including the metadata called the CID of the part, the spectrography, everything. Second, we have created the model with the hybrid approach, so combining simulation and the AI. Third, we created the root cause analysis with the AI model. We applied that model in order to prevent rejects and warn the operator. And in a fifth step, we provided recommendations to optimize the actual process. So in the fifth step, the operator receives concrete recommendation on new parameter set points in order completely to avoid the scrap. This was the setup. So basically, simply said, as I said, the most important topics are machine data and the quality data. And furthermore, we collected additional information like the mold geometry, spectrography, as I said, the environmental sensors like humidity, temperature, and all the air pressure influencing factors. And we combined it in one model using the timestamp and also the ID, product ID. That was the result after 3 months. So we reduced the scrap rate by 50% in the different areas, 35% in the visual inspection right after the casting. And at the end, in the X-ray, nearly 70% reduction in the final inspection. But this was not only the impact. The impact was much broader, because the 50% less rejects are contributing to a nearly 7% increase of productivity. And even more, due to the savings of scrap, it contributes to an indirect energy savings of above or nearly 5% on the whole plant level, which leads to an overall cost reduction of 6%. And that is the effect that we have to achieve just on one part that we have done in the first pilot. The second example is energy consumption, because as I said, it's not just energy management. It's not just monitoring the energy. It's about the correlation of all energy consumers, energy/power. We're talking not only about gas, we're talking about electricity, we're talking about also compressed air. So everything that is contributing to an energy loss is analyzed and linked with a timestamp to the production. And by knowing that, we are able to identify, for example, a deviation in the energy. If you produce a huge, heavy casted part, of course the energy will increase. But how do you differentiate if you produce a lower, less heavy part, and in a conjunction with a heavy part? You see just the energy consumption. So somebody must analyze every peak in the energy consumption in correlation with the product that was produced to identify, was it an abnormal energy peak or was it a normal because we produced a heavy part? And that is correlated with all the influencing factors, so the actual parameter and the set parameter. Why do we use actual and set parameters? Because we have observed in that example, for example, in heating element of a holding furnaces, there was an actual preset value of 35 kilowatt. That was the standard. But we observed that by regulating the holding furnaces, this heating element goes up to 42, 45 kilowatt. Just a single heating element. By not able to control that, nobody will take care of that. And furthermore, nobody was aware that the heating element is just turning on and turning off with full power on and zero. So, but there was the observation that there was not always the high power needed. There was only, for example, just 10 degrees difference that needs to be covered. The holding furnaces ramped up on full speed and high power on every deviation of the temperature. So by identifying that, we were able to identify the different areas of energy wasted in air leakages, in consumption by the idling time, and most of all, the consumption per produced part by 30%. Overall, on a plant level, that was contributing to 7.5% of energy reduction, just on that project. So, coming to the end. First of all, the takeaways for that, AI is possible to learn from data. It is correlating data and is working towards a specific target. Second, AI is possible to understand when it's developed right of the complexity of processes in the industrial and manufacturing environment. Third, the casting-specific technology that we have developed is able to optimize in real time the areas of wastes in rejects, energy, and productivity. And last but not least, the combination of physical simulation and AI with embedded process knowledge in each use case and each product that we have makes us, enables us to achieve results and first savings in the first 2 to 3 months after we have started a project. This I already presented. So yes, TIA is changing everything, but the good news is you don't have to change everything. Why? Because TIA is a non-invasive process. So your production processes can stay as it is. You do not have to change anything. The only thing that we add on is the augmentation by recommendation, by prescriptions that we provide on the machine, on every operator. Thank you very much.
Thank you, Jurgen. Any questions? Go on, Dave. The question is it important for experts to decide the combination of simulation and AI and what parameters to measure?
That's for me,
So
Trevor.
is it important for the experts to decide the questions to ask in terms of the AI?
Which experts? Foundry experts. No. So the foundry experts, so what is in the background is not important. It was just an illustration why traditional AI is not working in production processes at a certain extent. How a project usually starts is we sit down with the foundry experts and we draw the Ishikawa. This is what you know, right? And you are the expert in that process. We are not the experts in your process. We are the experts in applying the data coming from the different sensors that are responsible and important to collect in an artificial intelligence and model that. So the questions that you have to answer, you know already. What are the most important influencing parameters? The second question that we have to answer together is, do we get the data? Do we have the sensors? Do we have the PLCs that provide the data? And if not, how can we get the data? Can we install additional sensors? Can we open up the PLC to get the information out of the PLC? That is the question that we have to clarify together. But then we just extract the data.
Any more questions online? Just trying to keep me fit, aren't you? So the question here is a very interesting presentation, but how is the process data added to AI? Is it automatic or manual?
The data is, well, there's a first step of extracting the data. This is at the moment the most challenging point, because we are in the brownfield and we have to also respect the situation that data extraction was not the main issue. So first of all, we have to make sure that we get access to all the relevant data points. That's the first issue. As soon as we have them and provided an infrastructure to collect all the data on the shop floor and transmit it to our data cloud, then the data is processed by our AI models automatically. So the whole preparation of the data, the whole structuring of the data, the whole implementing of the data in our models is done by our experts in our model. That's what I'm saying about the domain knowledge that we have inbuilt, and that is done nearly automatically.
Any questions from the floor? Anybody else got any questions? Okay, I think that they're just preparing the food. So what I'd like everybody to do is don't forget to sign the registration form. And I'd like to call on Wendy to say a vote of thanks.
Well, I'd like to propose a vote of thanks to Jurgen for his presentation. I found it most enlightening. Please don't ask me any questions because I'm not going to remember it all. But I'm sure, I actually think that as technologies are advanced, more companies will adopt them within their processes. So I found it really interesting, and I'd like to put it to the floor to show our appreciation in the normal way. Thank you.
So again, I'd like to thank Jurgen for coming along this evening to make the presentation. It's something a bit different. I think we have to think about it. It's certainly, there are a lot of foundries already taking this technology on board and looking to utilize it to help them in the performance of what they're trying to achieve. So Jurgen, thank you once more. And that's the end of the technical session for this evening. Thank you.